Um, all right. So now we got that expression is equal to -2. And so now we can apply our, um, we can try to solve for a of x by, you know, uh, you know, just moving everything to one side and then solving for a of x as a normal equation. So, uh, so we have that equals to -2. Um, in other words, in other words, we have, um, we have a of x times 1 minus 2x is equal to -2 plus 3 summation 0, 0, 0. And so basically, we get a of x is equal to, actually, let's simplify this first. So this is a geometric series. It's a geometric sum. Um, that can be expressed as this, but where a of n is equal to 1, and if we move the 3 in, we get a of n is equal to 3. But the geometric sum formula has that 1 over 1 minus x is equal to um, you know uh, this, and this comes from the the geometric sum formula for the general formula for that, where we have 1 minus I think like a of n over 1 minus a, and in this case a is x, is equal to sum equals to 0 to n, I believe, yeah, of a of n. But in this case, we know that n is infinity, and for generating functions, we know that x is always equal to uh, we know that um, x is equal is in the range of -1 to 1, and so that's a decimal, so that's gonna make it smaller and smaller as it goes to infinity. So uh, the limit of that as n equals to infinity is equal to this thing is gonna be 0, and so we also know that, and so in this case, a is gonna be equal to x. So we get this formula where 1 over 1 minus x is equal to this, and equals to 0 to infinity of x prime n. And so we can express this as, we can use the formula, and we're gonna get this equal to -2 plus 3 times 1 over 1 minus x. And so now we can use, cross multiplication, and we get that this is also equal to, so we want to get -2 in terms of 1 over 1 minus x. So 1 and 2 times 1 minus x over 1 minus x minus 3 over 1 minus x equal to -2 times 1 minus x minus 3 over 1 minus x, which is equal to -2 plus 2x minus 3, I believe, over 1 minus x. Um, this is equal to 2x minus 5 over 1 minus x. Okay. Um, so yeah. I think it should be. Um, so this is like, wait, no, it's plus 3, right? So sorry. It's not -3, it's plus 3. Right. So applying the formula, we have -2 plus 3 over 1 minus x. And so now we do cross multiply and um, we get -2 times 1 minus x uh, plus 3 over 1 minus x. We combine, we have like, we make both terms have the denominator as 1 of x. This is equal to -2 plus 2x plus 3 over 1 minus x, which is also equal to 1 plus 2x over 1 minus x. And so now now we can use this, and so we have we divide both sides by 1 over 1 minus 2x. And so we have a of x is equal to 1 plus 2x over 1 minus x times 1 minus 2x. And so now remember that a of x is equal to this sum of a of n plus x power of n. You remember I said that if we found the coefficient of x power of n, we get a of n. And so now we're very close. We just need to express this expression as as a sum. How do we do that? Well, one common way is to express this as geometric sums. But to do that, we need to decompose this fraction. So we can use partial fraction decomposition. And if you're not familiar with it, feel free to check out a tutorial on YouTube, or if you want me to make a video on that. But you can using partial fraction decomposition, you get this over 1 minus. We get some variable a over 1 minus x plus b, some variable b over 1 minus 2x. So we're basically saying that it's going to be expressed in this form. And so now we just solve for a and b. That makes this equal. And so now we can solve for the equation, for this equation itself to find a and b. And so to do that, we can multiply everything by 1 minus x and 1 minus 2x. And so if we multiply everything by 1 minus x times 1 minus 2x, we get 1 plus 2x is equal to, if we multiply everything by those, then the 1 minus x cancels out for a, right? The term of a. And so we get 1 minus 2x times a. Plus, and for the b, the same thing happens. Like if you multiply it by 1 minus x times 1 minus 2x, 1 minus 2x cancels out. You can cancel out the values, so we get 1 minus x times b. And so now to solve for a and b, we can plug in any value for x. And so I would probably plug in, like to solve for b, I would plug in 1/2, right? Because I want to get this equal to 0 so that we get an expression for b, equation with only the variable b. And so if testing for x equals to 1/2, we get 1 plus 2 times 1/2, which is equal to 2. Is equal to 1 minus 2 times 1/2, which is equal to 0. A plus 1 minus 1/2 of b. This is equal to 0 because 2 times 1/2 is 1, and 1 minus 1 is 0. And the left side is equal to 1. So we get 2 is equal to, because 1 plus 1. We get 2 equals to 1 minus 1/2 is 1/2, so 1/2 b, or b is equal to 4. Right. So now we need to solve for a. To solve for a, we do the same thing by plugging in x equals to 1. Because notice how if you put x equals 1, the b term becomes 0. So we have 1 plus 2 times 1 is equal to 1 minus 2 times 1 times a. Plus 1 minus 1b. To 1 minus 1b equals 0. The left side is going to be 3, because 1 plus 2 is 3. You have 1 minus 2, which is -1, -1 times a. or a is equal to -3. All right. So a is equal to -3. A is equal to -3, and b is equal to 4. And so uh, and so from this point on, we could use the geometric sum formula here um, to both of these in order to obtain a sum, right? We have a of x is equal to -3 times 1 over 1 minus x, and then plus 4 times 1 over 1 minus 2x. The 1 of x, 1 over 1 minus x, we can substitute this with this. We have, you know, equal to -3 times the sum of x power n plus 4. And so now we have the -2 on the bottom. So uh, that would be the same thing as like for this, using this, we substitute x with 2x. Uh, so like we have like 1 over 1 minus 2x, where like we substitute every x with 2x, which would mean that 1 over 1 minus 2x is equal to this and 0. And we literally substitute every x that we see with 2x. So we have 2x graph n is equal to sum of n equal to 0. 2n times x graph n. So we have also that 4 times, so we also have that this equal to 4 times, sum from n0 to infinity of 2n xn. And then if we move the -3 and 4 to the inside, we get sum of n equals to 0, infinity of -3 times x prime n plus 0 to infinity of 4 times 2n times x prime n. And now we can combine these into one sum. Because you remember again that we wanted to find this, right? We wanted to have express a of x, which is the generating function, into its summation form, so that we can find the coefficient of x power n to get the general solution. Not yeah, like the general solution for a of n, which would be its explicit formula. So um, we want to combine this into one sum. And so this is also equal to, we combine this into one sum. Let me just erase this now. So combining that into one sum, we're going to rewrite this sum. Okay, so write this is one sum as, because they have the same index. Well, you remember last time there was like one term with n equals to 1, so we had to account for that by taking out the n equals to 0 terms. In this case, we don't have to do that because every term is already in the form, and we don't have an extra x. So we have that, -3. So we start with -3x and plus 4 times 2 to the power of n times x to the power of n. And so now the last step that we have to do is basically just express it in terms of x to the power of n times something to find a of n. So equal to that to the power to infinity, we have x to the power of n times -3 plus 4 times 2 to the power of n. And so now we know that the general form for OGF for a of x, we wrote above that it was equal to sum of n equals 0 of infinity x to the power of n times a n. And so now we know that these two are equal, right? Because we put it in the same form. And so we have solved our recurrence finally. That a of n is equal to -3 plus 4 times 2 to the power of n, which is also equal to 2 to the power of n times 2 to the power of 2, because 2 to the power of 2 is equal to 4, right? Minus 3, which is also equal to, we use the exponent formula, the exponent rule for these two, where if you're multiplying, then we add it. So we have 2 to the power of n plus 2 minus 3. And there we have it. We solved our linear recurrence. Yeah, it's very cool, a very cool trick. Very cool way to evaluate linear recurrences. Just take a while, but yeah. And if you want to test out if this works on the recurrence, let's test out like two values, right? So the first value, let's recall the recurrence right here. We have let's try a of 1. A of 1 is equal to because we substitute every let n equals to 1. Then we substitute every n with 1 to a of 1 minus 1, which is also equal to a of 0 plus 3. And then we know that we were given that a of 0 equals to 1, so we have 2 times 1 plus 3 is equal to 5. For n equals 2, we have a of 2 is equal to 2a of 2 minus 1, which is also equal to 1, plus 3, which is also equal to 2 times 5, because we just found a of 1 is equal to 5, plus 3 equals to 13, right? But also using our formula, we get that a of 1 is equal to 2 to the power of 1 plus 2 minus 3 goes to 2 to the power of 3 minus 3 goes to 8 minus 3 is indeed equal to 5. So that's a very nice thing, that our recurrence works for n equals to 1, for n equals to 1, and for n equals to 2, we got a of 2 is equal to 2 to the power of 2 plus 2 minus 3 is equal to 2 to the power of 4 minus 3 is equal to 16 minus 3, which is also equal to 13. So our linear recurrence formula works. That means we have solved our linear recurrence. That's a pretty pretty amazing result. All right. And that's all. Thank you for watching. And have a nice day.